What up, physics folks? I'm here to talk to you about Unit 1, Worksheet 4. I do just want to give you a brief overview of things and give you some important pieces of information related to what you have to do on this worksheet. So there's something that I want to write at the top that will be helpful as you go through, or I'm going to write a few things at the top. But the first thing I want to write is a just quick kind of definition for period. I know we've already defined it, but I want to define it in a more specific way. And the period is going to be the number of seconds for one cycle. So period is always the time it takes for a cycle, and more specifically, we're going to say the number of seconds for one cycle. And then there's a new term that I want to give you that you've heard before, and it will definitely be discussed quite a bit as we talk about oscillating motion and waves, but is the word frequency. And frequency is very much connected to period, but it's kind of the opposite of period, or in fact, it's the inverse of period. It is the number of cycles for one second. So once again, period is the number of seconds for one cycle, and frequency is the number of cycles for 1 second. Which means, because they have this inverse relationship, we can say that period is actually equal to 1 over frequency, which is noted by the letter F. And frequency has units of what are called hertz, and a hertz is actually equal to 1 over second. And so anytime you see frequency, you can assume that it's in the unit of hertz, and the unit of hertz is 1 over second. So let's just write that there. Okay. One other thing I do want to write down, and this is from the lab, and this will also work on this worksheet, is yesterday's equation that we developed that related period with mass and the spring constant. And if you remember correctly, if we increase the mass, the period will increase accordingly. In fact, it will increase by the square root. If we increase the spring constant, the period will decrease accordingly, and it will decrease by the square root of that change. And so as you're going along this worksheet, you will see that you will have to do things with period, and you will have to do things with frequency, and you will have to do things with amplitude. One thing I'll point out is the amplitude is how far let's see, the maximum displacement from equilibrium. And I'm kind of all over the place here, but it's all good. So the maximum displacement from equilibrium. So say something is stretched 30 meters from that middle position, that equilibrium position. That means the amplitude is 30 meters. That's the maximum point it would get to, the maximum displacement it has. And so amplitude will be part of it. And then as you can see, looking at the period, speaking of amplitude, amplitude is not in that equation, so you should remember from the lab that amplitude had no effect on the period, and so that will do nothing to the period. So anyways, so you'll answer these questions on the first page related to everything that I wrote at the top here. And then when you get to the second page, you get to do the fun wave graphs again. And so the position versus time graph is given to you. And so from that graph, what you need to do is a velocity, acceleration, and a force wave graph, which you've already done. But then there's two new ones. You have kinetic energy, and you have elastic energy, and then you have total energy. And so one thing about total energy, hopefully you can remember, is that if there are no external things that are taking energy away from your system, in this case the system would be our box and our spring. If there's nothing like friction taking energy away, the energy should stay the same the whole time, but just change from kinetic to elastic energy. Now, kinetic energy, if you recall, is related to, oh, come on, is related to, oh my gosh, velocity. In fact, it's 1/2 mv squared. So as your velocity goes up, your kinetic energy goes up, and as your velocity goes down, your kinetic energy goes down. And if your velocity is 0, then your kinetic energy should be 0. And then the elastic energy, EEL, is related to how far it's displaced from the equilibrium position. So if it's at the equilibrium position, it's not displaced, so that's when elastic energy is 0. And when you're at your maximum points, to the right or left, that's when your elastic energy is the biggest. And just one quick little note here with those, notice that kinetic energy is related to velocity squared, and elastic energy is related to displacement squared or position squared. That means if you are squaring how far the position is away from equilibrium, that makes elastic energy always positive. And if you are squaring the speed or the velocity at which the box is moving to get kinetic energy, that means your kinetic energy is always going to be positive. And when you're looking at these kinetic energy and elastic energy graphs, anything below the line is negative and anything above the line is positive. And so if you can't have a negative kinetic energy and a negative elastic energy, where should the wave never go? All right. So I think that's all I really have for now. I'm going to give you guys time to work through this, and then you'll have solutions posted at a later time. As always, please ask questions on Google Meet. Please ask questions on the discussion board. Please ask questions over email. Whatever you need to do, just ask questions if you don't get it. Good luck.